Okay, so very good evening to all the participants and welcome to the fifth day of the AICTE ATAL FDP on future perspective of AI and data sciences, algorithms and applications. For this session, we have with us Madam Soma Bandyopadhyay as the guest speaker. Before she starts her talk, let me take the privilege to introduce to her. Madam is Senior Consultant of Tata Consultancy Service, TCS, Research, having a role of Senior Scientist. She has more than 26 years of industry experience in the research and development areas of real-time embedded systems, Internet of Things, AI-based sensor data analysis. Currently, she is working in the area of sensor data and data analytics like identification of pattern events inside the sensor signals, lightweight learning with less level and limited data, generative learning for synthetic sensor data generation, unprivileged and representational learning. She had been earlier with Revika Technology, MacMet Interactive Technology, working on real-time embedded systems in area of interactive TV and set-top boxes. Its different device drivers, real-time operating systems, digital signal processing, communication stack. She has also worked with Digitech and Indian arm of digital technology, Bedford, US, previously owned by the Agilent, uh, Agilent, working on development of embedded protocol stack, different routers and ATM switches. She has published several papers with H-index 22 as per Google Scholar. She has 40 plus granted patents. She is a BTech and MTech Computer Science and Engineering, BSc Physics from University of Calcutta, India. Currently, she is pursuing PhD in Artificial Intelligence from IIT Kharagpur. With this small introduction, I would like to hand over the session to Madam. Welcome, Madam. Madam, please start.
Okay, thank you. Am I audible?
Yeah, yes, Madam. You are audible.
Yeah. Okay, so thank you for the introduction and thank you for this arranging this session to deliver this talk. So I would like to start sharing my screen to this topic, what is our interest today. In case if you have any question, you can ask me at the end and I maybe stop a video. You may also stop me in between, but for the sake of flow and time, it would be better to take the questions at the end, maybe.
Yeah, that is what
And
we plan, Madam. Actually, 1 hour 50 minutes. If you tell, then next 15, last 15 minutes they can ask. This interact with you.
right. And the other point is that I miss, sharing video. I may stop if I'll see that there is some issue is coming because of some, the bandwidth and all.
No
Okay.
problem.
Okay, so now I'm sharing my screen. Just let me know whether you can see it or not. But I don't know how to share it from here. So, what is the sharing option here?
As in the screen itself, you can find an up arrow is there in the bottom part. The bottom switches are there. From there, the up arrow is there. There is a hand symbol, and before that,
Mhm. Just give me 1 second, just to
yes, yours.
entire screen. Can you see the screen?
Hmm, not yet appeared.
No. Acha, let me share a window. Only system preference. This one you can see. Actually, okay, just let me see. Choose what to share with me, google.com. Okay. So window, entire screen, then only system preference. So only system preference is okay. Google Chrome, let me try. Hmm. I don't know whether it will work or not. Letter. Still, you are not viewing the screen?
Still it not appear, madam.
Okay, okay. I don't know why. So, can you please tell me that how to do this? I went to this up arrow.
Yeah.
Okay.
Up.
Click on the dotted up arrow. Yes.
Hmm.
Click on the dotted up arrow. Then
Then there is a Chrome tab, window, and entire screen. You can even use entire screen also fine. Enter screen and
no.
then click.
See, someone is actually sending some message. So, if you join via companion mode screen, sharing is not allowed. Companion mode screen. I don't know. What is that? To share your screen, allow screen recording for Chromes in system preferences. You will need to restart Chrome.
No, not.
Is it required?
Uh, not required. I mean, just you can. I mean, it will be very easy. I think just you can go to that up arrow and then there will be a window will appear. With that, three options are the Chrome tab, window, and entire screen.
Right. Right.
Then just
So what
entire screen you can click.
that's only I'm doing because that's the way we do in Teams. Then,
Yeah, then click to the entire screen in the area.
huh?
Mm. Then share it. That's all. Below is the share
No,
option.
there it is not. It is asking me to share your screen, allow screen recording for Chrome in system preferences. You will then need to restart Chrome. That's.
Uh, that you can no need to not nothing to choose. I think
No,
better not.
I have given Chrome a permission. No. Okay,
Okay.
let me just rejoin once.
Madam, maybe you are using the MacBook. I think, right? You're muted, ma'am. No, unmute yourself. Is it MacBook, ma'am?
Yes, yes.
For that, you need the setting that you have to allow through the setting.
I did that. I don't know
Okay.
what is happening. That's
Otherwise,
why.
if you send the PPT through mail, I can also share from my side.
Mhm. Okay, just give me some moment.
Yeah, fine.
Yes, disgusting. Just let me see. I have tried all options.
Okay.
Entire screen, window, open system preferences. Then it is whatever the thing it is saying. Uh, Privacy and security. Screen and system audio recording. Google Chrome, I have given the permission. Uh, Google Chrome will be able to record the content of your screen until it is quit. Do not choose to quit Google Chrome or do it quit.
Madam, you are muted, I think. Ma'am, you can share, otherwise PPT I can share. You can present maybe. I can't hear you, ma'am. Actually, you're muted. If you're saying something, I can't hear you. Unmute yourself.
Can you share something? Can you
Okay, you
share?
have
Can you see my screen now? I'm sorry.
yeah, no, 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 not yet any sharing screen is there. No, no.
But I have enabled this thing.
Okay.
Yes, can you see now?
Not yet come.
Oh, did come.
Uh,
Actually, this is something I feared. That is
okay.
why I send you an email because from my office laptop, I can't use Google links. This is
Okay.
my personal laptop MacBook. So from there, I just trying.
Understand. Understand. Okay.
Let me try.
Okay. Okay.
I have given all permissions. Can you see my screen?
Now
I,
it is, I think, appearing. Yeah, there is another screen coming. Yeah. Yeah. Correct. Correct. It's coming.
okay. Sorry, and my apology because
No, no.
I'm very extremely sorry for the people who are waiting because time is very precious. Anyway, so this today's talk is on DL-based generative models for sensor data synthesis. So at any point, can you see now my screen?
Yeah. Yeah. Your
But
screen is
you
there.
can't see the
But
mm,
slides, the
slides are not
presentation part.
there.
Mm-hmm.
Slides you
Slides.
can't see.
No, it's just Google Meet only just shared now.
Just
That screen.
wait.
Only the Google Meet screen I can see that. The slides I cannot see.
I-
You have shared the entire screen.
Yes, yes. Just a moment because uh, shape from here. Um, Stop sharing. Then here, if I want to share entire screen,
Entire window. I mean entire. Uh,
no, entire screen.
Entire.
Entire screen is of what?
Yeah, and I think it's now appearing screen.
My
Yeah,
screen?
yeah. Yes, now it is the slides are visible.
Yeah, okay, fine. Okay, so today, sorry, I'm now starting the talk. So today's talk is actually on the DL-based generative models for sensor data synthesis. So what is happening now in this mode? Okay. So the agenda is first we will discuss on the importance of sensor data synthesis and some of the exemplary scenarios, and then we will go to the methodology and different application and case studies.
You can do full screen, ma'am. No problem.
Yeah, that is what I tried.
I think the three dot is then on the right hand side. Three dots and then the one is this one.
Is
Yeah,
it
that's
okay?
fine. Yeah, it's fine.
Okay. First, let us start with the importance of sensor data synthesis. And to understand the sensor data synthesization's importance, uh, let us first see some of the applications of sensors. So nowadays, there are very, I think, important applications which are all sensor based, like remote sensing, where we are going to have use different kinds of sensors which are having the different kinds of electromagnetic spectrum like NIR, optical, microwave, RF, radar, etc. Then we have the different physiological sensing which are very popular to our day-to-day life, like IMU sensors, which are basically inbuilt in our mobile. Then camera, GSR, etc., along with the temperature sensor. Industrial sensing, we use different kinds of vibration sensors to detect whether there is any kind of fault happening in the system, to increase the life of the overall machineries and setup. The industrial sensing plays a very important and key role. And the other one is this navigating sensors like GPS, which is a very common and again a very popular sensor for our life, where we all the time use this Google Map and all, where we use extensively these GPS sensors. So these sensors are nowadays getting applied to a wide varieties and wide variety of applications. So along means with this, I'm going to set the context, the need of sensors and the applications, its diverse applicability towards the different applications. Now there are different challenges these sensors are facing. I mean, this application of sensors are facing. First of all, the challenges are like, for example, there are all the time maybe that the sensors data collection we have to face through a lot of hurdles. So there is limited experimental data and ground truth. At the same time, it may happen that we have a lot of data. Somehow we have managed to collect the sensor data. However, there is not available ground truth with it. So let me give the examples of it. For example, that collecting the data in sleep labs, EEG data, to identify or to get an inference about the sleep disorder. So putting the cap and then collecting the EEG data is anyway a very boring task, and it is very difficult to collect the data. So there is always a limited kind of data we are getting. I'm giving one example of this, but in general, collecting the data from the sensors are really challenging. So we always have a limited data with it. And even say, for example, that we can collect the data. For example, for the activity monitoring, we can collect the data from our phones. And for example, that we are walking and running, we are collecting the data, it is fine. And we are even tagging the ground truth. But it is very difficult, say, for example, when I'm biking, in that stage, it is difficult to get the ground truth. We may collect the data. So there are means one very, I think, unavoidable challenge is limited experimental data and ground truth that data applications are facing. Secondly, sensor data are handling actually sparse and low frequency data, because there are all the time, means there are some situations that sensor data are sparse, or for example, that we are getting a low frequency data because of some battery problem, some sudden shutdown. Many of the cases, it happens that for all the time period, the sensor data are not getting captured. So there is a sparsity issue which is inherent with the sensor data. There is also another challenge, that is exploration, that is the unobserved states we used to face. So to explore those unobserved regimes, means it is always we have to have a inclination to get the data from the observed state to unobserved states. And definitely to capture the complex pattern from the sensor data is anyway the very important aspects to get a applications which is actually performing up to the mark what we looking for a specific task. When we do that time, we are looking for a looking for an application which should perform as per our expectation. To get or to meet that expectation, we should identify the complex pattern inside the whatever the sensor data is having. And so this, with this limited experimental data and ground truth sparsity, and there are unobserved states in many of the states, it is difficult to collect the data, even though we can collect the data for some of the states, but some of the unobserved states we can't. In this I think presentation, I do have some slides on it. And the third one is that we have to understand the complex pattern of the sensor data. Now, the important part is that which we should, I think, keep in our mind, that sensor data synthesis, when we will do, we have to understand the way the data is getting generated. That is the system or the physics of the sensing system. It is very important to do this sensor data generation, the generated data to be meaningful and to be close to the real. We should have the understanding of the physics or mathematics, how this overall system works when the data is getting generated from the sensor system, I would say. Is it okay? You can hear me, right?
Yes, ma'am. You can hear. We can hear you. No problem.
Okay. Now, going to the next slide, that what are the different salient aspects this sensor data generation is going to have? For example, that we are generating the sensor data. One can generate the sensor data, but what to do with this? We have to be very focused about its application, that what is the end goal of this sensor data. When we generate this data, where should we apply that? Because that application demands some kind or some specific need to be accurate during the data generation process. So we could use this generated sensor data for the data augmentation. For example, that I said that there is a limited data, so we can augment for a specific class. For example, that we may have a less data in the biking scenario, and we have a lot of data in case of running and walking states for the activity of human being. So we can generate the data for this biking scenario with a limited sample, and then it works as a data augmentation for the better inferencing for some better task. Now there is another aspects where the data generation are handled to address the missing data scenario or the data for the unobserved states, which we do not have the data. It is very difficult to capture the data. It is not possible for collect the data in practical scenarios. Then the third aspects is the data generation. When we do that, is getting uh, a focus that it is to be used for some kind of domain adaptation or cross domain data generation, we may say. I think which is a very important aspects in today's the way we are moving and applying the AI, and specifically these generative models are getting exploited. So cross domain data generation for the sensor scenario is very applicable and demanding. Now what are the the task we could do with this? So to improve or to achieve classification performance improvement, say for example there is a sort of class imbalance, some of the classes is having less data, so we could augment the data and improve the performance of the classification task. Similarly for the prediction task, recommendation, if we have a some states which are sparse, for those states we don't have the data, so if we can generate the data for those sparse states or unobserved states, we could do better recommendation, and this recommendation task is applicable for any domain. Then the privacy preservation, this is also another important aspect. Let me tell you one example, that for example the GPS data, it is very privacy sensitive data. Now this GPS data, when we collect, we actually take the information about the user, even though it is anonymization is done, but we need that data for this user ID and all, because to get that thing. But in the randomly, if we can generate the data considering some of the user samples, so we could have a large amount of data where there is no user's name and nothing, no consent, nothing is required. So this is one example where for the privacy preservation, the data synthesization from the sensor is actually applicable. And the other part is that the counterfactual reasoning, this is definitely a causal aspects, where in the scenario when we want to get the sensor data, which is not actually in the real sense, but we want to do something which is counterfactual. So in that case, how this data generation is getting applied or applicable, that is another important and interesting aspect where the sensor data generation is going to be used. So far we have seen that what are the different applications of sensors, then what are the challenges these applications are facing. Then if we want to generate the sensor data for those applications, what are the different aspects we are going to cover. Now let us take one examples scenario. So this is an example which is very common to our day-to-day life, where we are seeing that one person is basically walking, another is running, another is biking. So here the important part is that if we have, say for example, as I said, that collecting the ground truth, it is very difficult for the biking scenario, let's say. So if we have the sensor data generation model, where from the walking and running we could generate the data for the bike scenario. So for that, as I said, it is an example of cross-domain data generation, definitely. And at the same time, which is very important for this sensor data synthesis, is that we should understand the physics or the way the whole system works. So that knowledge we have to acquire during the sensor data generation. In this case, the variation of accelerometer sensor. Now, this is another example that the sparse data, as I said, is the radar data. So from this, we can go to the high density data, low density data to high density data. We are using in this scenario to densify the data, which is very much getting used for the remote sensing. This is also a cross-domain sensor data synthesis scenario. In the remote sensing cases, this is from the LiDAR to radar data, or it could reverse path is also important. So basically, in some scenarios where LiDAR data means this radar is very much easily obtainable in a way. Uh, for example, that in mining, where we were looking for some kind of automated mining process where the human intervention is very less. We could have the robots who is having the the radar sensor, and then it's moving around to detect the objects in the mines. So in that case, the difficult part is that, as I said, that radar data is faced by the, in previous slide I was showing you that there are uh, sparsity with it. Lot of things are getting missed, and so it's a low density data. So if we somehow going to manage to have some kind of ground truth with LiDAR, then it is, if we try to having that small radar data, how to get into this LiDAR to radar, which is a cross domain data generation process. So this is actually to facilitate these three examples, that what are the different kinds of examples we are facing. But every places what we are noticing that we have to understand very much about the sensing system, how it operates, what is its physics, what is the knowledge, the way the whole system works. So that knowledge, that could be in physics knowledge, that could be in some kind of mathematical form, or some kind of causal aspects. So whatever be the knowledge that we have to acquire during the sensor data generation process. So now let us go inside directly to the methodology. So first of all, then the key aspects what we have seen, that the data generation, what we have to keeping in our mind. One is that synthesization for unobserved or difficult to accessible or challenged accessibility constraint state. Then as I mentioned, that the domain knowledge adaptation, which is very, I think, important part and key aspects. Then handling limited real data and at the same time limited ground truth as well. And definitely the low resolution to high resolution data, that is the handling sparsity, is an important aspect, what definitely the sensor data generation should be looked into. Now here we try to address that the data generation process by using these deep learning based generative models, and I'm going to walk through few of them. So first of all, this DL based generative models, I think this is something giving training data, and mainly generative models are working from a probabilistic space and then performing the sampling. The one of the important model, I think, for the sensor data generation is this variational autoencoder and its different kinds of variants. So this we have this I have taken from a tutorial. So this picture. So here the main part is that the model, when we give the data, it encodes the complete information in a sampled space, which we call as a latent representation. And from that latent representation, whatever the important features, those are getting captured. So the part which captures this important informations and performs this encoding to the latent space, that is known as the encoder. And then from this encoder, when this latent space is getting generated, this is getting sampled from a Gaussian distribution, and the data generation happens. Just a reverse block, which plays an important role to get the data back from this latent representation space to the output or the generated data or the predicted output. This specific model could be applied as a generator, could be applied as a predictor as well. Means we can get only one sample or we can get a number of samples. So the sampling space, which we are saying as a Gaussian space, so from there we are getting this generated data where this latent representation takes a very major and critical role. Generally in a variational autoencoder, its objective function is that in any DL network is a functional approximator, but during this approximation or during this specific task when it performs, it must have some kind of objective. So that objective is known as the loss function, objective function, etc. So here it has the two components. One is the mean reconstruction error, which is generally getting uh, uh, by using the mean square error loss between the input and the generated output. It could be categorical cross entropy, it could be many other things. So one is this reconstruction loss part, reconstruction error we used to say, which is actually the difference between the input and the out generated data, the output data, and where it follows the values. And the other part is the difference between the distribution of this input and output space. So that is basically the scale divergence loss, which is scale divergence is a measure which do the data distribution difference calculation. So this reconstruction loss and scale loss is the two major components. After that, there are many different variants are coming up. Specifically, in case of sensor data generation, this conditional variational autoencoder is taking a key role, where along with this latent space, along with this X, it is also getting conditioned on the whatever the condition we are going to provide. With that, it is also getting used. Now there is also another important I think concept with this variational autoencoder, which is known as the uh, scale annealing method, where dynamically we can fix the time, meaning the fix the number of epochs, where we can focus only on this reconstruction part and but not the scale divergence part, and after some time both of them should start working. So the scale annealing is very much applicable for the very critical, very much applicable for the data, which is a complex data, I would say, where it has a lot of complexities, complex patterns inherently with this. So along with making this encoder strong, the scale annealing part is also another important aspects. And I must mention one another part, that this variational autoencoder is inherently faces a problem, which is like a stochasticity. And for that, the gradient flow is getting interrupted for this two statistical parameters when is to learn from the data, which is the mean and the variance, mu and the sigma. So this mu and the sigma, but there is some kind of tricks used to applied, which is known as the reparameterization trick, where this one small term are taking into consideration, which is known as the epsilon. So that is actually taking into account to get the data from that epsilon is sampled from the Gaussians or the normal distribution space and getting multiplied with the sigma. And that's the way the whole thing works. So it's a very interesting model for this sensor data generation part. Many kind of domain knowledge, physics, many other kind of rules, etc., can be applied as a condition. Now, going to this generative adversarial network, it is a very established and popular network, mainly, I think, worked with this image space for a long time. So it is a sort of adversarial in nature, which is having a generator and discriminator. These are, I think, major two components, and definitely one is for generation part, and another is to make sort of making one component to make other component full, and that the way this adversarial loss works. So now, after getting these two major, I think, model, let us see that how we can do some kind of domain adaptation or the knowledge infusion to these models, which is in standard. It is actually common to VAE or GAN or other models when we are going to choose. But let us take some examples to understand this scenario. So one thing is that. For this domain adaptable part, there is, let us for the make it clear that we have to now deal with the learning process, that when we are going to generate the data, because this time the learning is going to play an important role. Learning means when the model is getting trained. So here, that this example what I'm presenting here, you can see this specific block, which is customized loss function, which actually takes this domain specific knowledge or the domain adaptation. So these specific components are playing an important role to adapt the knowledge for the specific domain when we want to generate. For example, that we are walking and want to generate the data for the biking. Now, I'm now going to present a functional block diagram, which we can consider as a generic block, where we are considering some physics knowledge as a part of the domain knowledge. This could be example of any kind of knowledge. But as I said, that this physics knowledge, physics in a sense that the knowledge, the way the system works during the data generation, that knowledge when the data is getting generated, what is the main philosophy this specific data generation process carries. For example, when it is a sort of data we are generating from an optical sensor, that time it is very crucial to understand the relation between the refractive index and the way that generation is, the way the light is getting propagated from the optical sensor. So the refractive index of the material and how the relation is followed, considering the light incident and all, is very important to know. And if we capture this knowledge during the data generation process when the model is getting trained, that time then while generation, when we get the output, that specific knowledge is also going to be there so that we can get some kind of realistic data. So that is the important block what we are seeing, that the physics guidance, and the main part is that we compute the variations of domain adaptable features. Whatever the domain features are getting varied from one domain to another domain, let's say for example biking, when the person is walking and doing a biking, so variation of acceleration is depending on accelerometer sensor is actually depends on the speed and the acceleration process. So they must have some kind of relation is getting hold there. So that is, if we understand that feature, say for example that feature 1 is changing linearly from domain 1 to domain 2. So if we encode that, or if we try to regularize or constrain our data generation process towards this, then that domain adaptation will happen and we are going to get our expected um, expected, I think, performance for those specific states where we do not have the data, whether it is a sparsity state, whether it is a cross domain adaptation. In that case, we are going to have it. Now, we are giving you that this is one of the example, that is, as I said, that we are going to discuss one example, which is a unobserved or the sparse state case scenario. It is a scenario for the progressive fault case. For example, that we can see the normal state and the complete failure state of a machine. But we do not know that when the specific fault progresses to its different states. So for these intermittent states, data is not with us. However, we have the data for this normal state. So from this normal state, when the specifically the fault progresses, so if we have the data for those scenario, in that case, we can increase the remaining useful lives in situations, like we can predict that uh, means or stop the machine complete failure. We can predict that in this time the machine is going to fail, so we can stop the failure, we can actually address the reason why it is failing, and somehow the overall system machines health are getting improved. So this is a very important, I think, aspects for the intelligent machine handling. And there the unobserved states data, specifically this fault progression scenarios data, if it is possible to generate, then the overall inferencing or overall model when we build with this generated data and the actual data, then it would be very strong in nature. To the model, the prediction model would be very, I think, in high performance we are going to expect. Now, the point is that from this normal state, when the fault progresses, how we'll do that? So we have to understand the physics, or we have to understand, acquire the knowledge that how this system works in case of faulty state and in case of the normal state. And what are the specific feature this is getting reflected. So with that, this is, I think, one of the example what I'm showing you at the moment, which is basically using this variational autoencoder. And then as usual, we have these two losses, for example, in these cases the normal VAE loss. And in previous slide I have shown that in case of uh, domain adaptation, cross domain adaptation scenario, when we have to acquire some physics knowledge, one of the method is constraining the data generation process towards that objective. And for that, some of the features which is in observed state, which is in a specific state or specific domain, domain A to domain B, if we understand that how these are changing, and if we can follow that, our data generation process, if we restrict that generated data should follow that specific, I think, that specific objective or that specific methodology. In that case, that is getting a part of that constraining is getting part of a term in the objective function or the loss function, which we called as a regularization term. So you can see that there is a domain adaptable feature loss is getting added with this. So these two are the, in general, the model that this reconstruction and the scale divergence. Along with that, we have a domain adaptable feature loss, which actually responsible to generate the data for those specific cross domains. And in this case, it is the unobserved states as the fault progress states, different faulty states, states 1, state 2, state 3. And this is a, in general, this is a, I think, the figure, whatever the domain adaptable feature, it is the generated and the input and the generated data. Along with that, how this reconstruction loss is there, and then the scale divergence loss is getting added with that. Now we have now got some idea about the sensor data generation, which is one of the important thing, is that how this capture the system knowledge or the physics knowledge inside the data, which is actually at the part of the sensing system or the way the sensor works. Now let's say that we successfully generated the data with this regularization. However, which is very important, that is validation. How do we validate the data, that whether we have done the data generation correctly or not? So there are standard formulas for the different kinds of evaluation metrics. I think all of us know that MSE, correlation, cosine, that is when we generate the data, we can do the comparison with respect to the generated data and the input data. However, I would like to give you some more examples. One is that, which is very, I think, important and interesting, that when we generate the data from taking some small samples of the input data, so the input data we can divide in train and test, which is the part of the original data. Now we could have a classifier which we train with this input, which is original, and we could test with the original test data the way we do. And we do a specific task. Here we have taken an example of a classification task. So we and capture the benchmark performance. And then what we should do is that we make another model, we train that classifier with that generated data. However, our test data is from the original data, whatever the test data, that we will not touch. So we do this inferencing using that original test data. So now we have a benchmark performance and the performance using the generated data when we train it. And then if we do the comparison and if they are close, then we can do this we could conclude that yes, the generated data is good in that sense. But sometimes we have noticed that if we use a very powerful classifier, then even though you have the some kind of noise, some kind of, I think, differences with respect to the original data and the generated data, the classifier itself manages somehow if you have a strong classifier. But if you do some kind of KNN based classifier or so, then this just sort of distance measure, then you can actually get that idea that how they are close or not. But there is other aspect which is, I think, very important for this sensor data generation part, which is unsupervised in nature. That is something, for example, that if we can make a cluster. Here we have applied a clustering by using one of our method which we called HCACS, hierarchical clustering on the auto-encoded compact sequence, which first we do a auto-encoded compact sequence of the data and do the hierarchical clustering. But it could be the K-means cluster or some other standard clustering technique to see that the generated data and the original data are false in one cluster. So that's an unsupervised way to validate. If they are falling in a same cluster, that means that they are very close with respect to each other. So that is the way we can validate the generated data's quality. Now let us quickly see some of the examples. So I actually given the data generation process, I have given the examples of fault progression part. So this is, I think, one of the work we did, and I would like to present the results. The fault progression data generation, where we have taken the data from this University of Connecticut gear fault data, and there that data we have actually synthesized for the unobserved state and do the validation. The getting the real data for the unobserved state, it is very challenging in publicly, first of all. And if someone is having a big system setup, they can generate for the validation, and that would be really useful to do. However, we managed to get one such data, which is a very, I think, enriched data set in that sense. And we have done this analysis by using our method, what I have just said. So here the main, I think, task of whole thing, that domain adaptation feature, which I mentioned in earlier slide. Here the main part is that, as I say, that when the data is getting uh, generated by a model, we have to understand that originally how the system works. So when the fault progression happens, how it happens, that time we have to see that from the normal state to this fault progress states, and then finally to the failure state, how the whole operation happens. What is the physical law or the mathematics behind it? What kind of knowledge we can get out of it? By the way, I'm audible, right, to all, and you can see in my screen. Hello?
Yeah, yeah, yes, yes. Yeah, we
Yeah.
can see here.
Yeah. So here the fault severity is actually the main factor when the fault progresses. So when a fault progresses from high, when say low fault, low severe state to high severe state, that means your fault is getting progress from one state to other state. Means the lower severe state to higher severe state means that your fault is getting progress from state 1 to state 2. And when the severity changes, that time the stiffness of that system decreases. So that is the first understanding we have to have with us, that what is the fault progression strategy. And then this stiffness parameter are getting, I think, you know, impacted or calculated by different other parameters, system parameters like teeth number, then teeth width, then contact ratio, pressure angle, Young modulus, Poisson ratio, many physical properties, and the importantly rotational speed of the system. Now we have to see that which specific factor or feature is getting reflected when we collect the data, input data from the normal state. So it is all about the system data when we collect. It is all about the means the nature of the pattern very much depends on the system frequency or the rotational speed. So we have taken the complete temporal data to the frequency domain and seen that how it looks like anyway. So this rotational speed is very important feature for this whole knowledge capture stage. Now, when this stiffness decreases, that time by solving some of the equations, what we have seen that when the stiffness decreases, the torque of the system in stiffness increases, right? That time the torque of the system that also increases. Then from that is one of the part. The second part is that if your rotational speed, how the rotational speed is getting tagged with this stiffness parameter, and rotational speed is how it is related with the stiffness parameter. So we are seeing that when the stiffness is getting increased, then finally this GMS frequency is getting increased. So oppositely, when the stiffness is getting decreased, meaning that when the fault severity is getting increased, that time the GMS frequency should be increased. And this GMS frequencies increase is getting reflected to the peak amplitude of the data when we see. So that is the way we have a paper on this, so that has been captured in detail. So the important part here to be noted is that we first computed this domain adaptable feature and then tried to see that how these domain adaptable feature are to be constrained when the data generation process is getting followed. So one of the examples is, as I said, that maximum peak amplitude. So how it is getting changed, what factor that has been first computed by plotting this by the different mathematical, I think, equations and the understanding of the system. Then we actually try to generate the data for the different faulty states. So if you notice that this is the less faulty state, 0.15 mm, and then it is 0.24 mm, and then it is 0.38 mm. Don't see the 5A, 4A, 3A, because that is the way the data has been given. But this is the fault, lesser fault to higher fault severities, and the data is getting generated. So here the important part of what I have just tried to depict, that the when we do this domain adaptation, it is very important to understand the system's physics knowledge and to capture that knowledge during the data generation as a part of regularizer in the overall learning process. Now, the second example is which I have chosen, which is a very, I think, mm, in the sensor data, which is a sort of not very common, but means commonly faced, very challenging in many scenarios, that we have the ground truth, but we have lack of ground truth, but we have the data. So how to automate this ground truth? So it is also a sort of data generation need, an application we can imagine for the sensor data, because it's, in many of the times it is very difficult to collect the ground truth in many scenarios even though we have the data. So this is also we have done by applying a variational autoencoder model. So this DL-based generative model is applied to generate the sensor data, where the main part is that we generated the data, and then when the generation happens, then we try to see the differences, and then based on that we reiterate the process. And in times we are first generating some noisy levels, and those impure levels we are purifying in the every stages. or through the every steps. So this is one of the applications for the sensor data, and this is a very useful application. And these are some of the results for the label generation process that I'm not going to, I think, discuss. Now, the different kinds of sensor, where are we, and with the generated label and the data, we try to do these comparisons. So we have seen the two aspects, which is the one of the applications we have seen that for the unobserved state, which is the fault progress state. Another applications we have seen that when we are trying to generate the data for the automated label generation, and the another case study which I actually, when I started, I said that, which is very, I think, important for the sensor data, and right at the moment, this is the way we are looking into the unobserved states is definitely a part of it. The examples what I have taken you through, that is this faulty state data generation, which is again a cross domain data generation, domain adaptable data generation process. So now this sensor data, we are trying to generate the data from one mode to other mode. For example, here we are seeing the video data, and taking the video data as input, how we can generate the data for the accelerometer sensor, for the IMO sensor. This is completely a cross domain data generation process, and this is a sort of I think aspects the sensor data generation is currently following, right? So this data augmentation part and all these parts are anyway there. The sparsity part is again, I would say, a sort of domain adaptation or cross domain adaptation part. Unobserved state is also another type of cross domain, and it is also another third last example what I'm showing you, that is the cross domain from one mode to another mode. This is a publicly available paper. We can see they have we have taken from a state of the art paper. So here they have actually combined the variational autoencoder and the GAN, and they have taken the conditional variational autoencoder from this. So this two part together, they have tried to generate the data for the uh, mm, one domain to the other. There are many other examples that I'm not showing. For example, that you have a season data. For example, that you have smart meter data for the summer, and from that summer you are trying to get the data for the winter. But again, for this cross domain, you have to understand that how, what is the pattern, that pattern you have to understand, that how the pattern is, and that pattern you have to I think, when you encode this pattern, you have to first analyze the pattern in a sort of mathematical form. For example, that how many houses are getting closed, what is the percentage, and that getting impacted to where. So like that, you have to have that thing. And there are also state of the arts available in many different contexts. And there are papers coming up from for example, this fMRI data, and then from the normal scan to fMRI, like this kind of cross domain generation is happening. I think there are some other cases people are talking about, that from the heartbeat, relation of the heartbeat and the EEG data. So many different aspects are coming up. And now I think there are some kind of sample codes you may not be interested with. So that is something I had for this overall session. Okay, so let me go back to my screen, and I actually ran one program also to just to show you that here you can see that what is the it is a variational autoencoder based code based on a data set which is a bearing data from CWRU. You can see that what would be the latent space representation by, and say for example that if you have a data, this is a data set, a bearing data set, where the bearing is normal and it has different variants of load. So this is the normal state data with the normal load. Now I can increase the load. There are some different ways. There are different types of faults are there, but at the most at the moment the model is trained with the normal data with different loads. So I could manage to generate the data by changing my condition with the different kinds of loads. Okay, so here I'm actually stopping my presentation. Thank you for hearing, and if you have any question, you can ask, and I would happy to take that. And sorry for the initial trouble what we have faced through.
Yep. Yeah. Thank you, madam.
LK
And
Shao raised a hand. I don't. Yeah. Okay. So can you please tell what you want to know?
Good evening, ma'am. Thank you for means a valuable session.
Thank
Ma'am, I
you.
have one doubt regarding that. You told reparameterization trick.
Yeah.
So, is it applicable for like when you are collecting real-time data, otherwise some like sensitive data?
Yeah, so basically, this reparameterization trick is a part of the variational autoencoder model. It is like the whole way this model works, it is having a stochastic nature, meaning that uh, it when the data generation means when the data learning happens, first you are encoding the important features, and then that you are taking into a representation space. Why it is space? In case of autoencoder, it is a single vector. We are saying it as a space because it is a distributed space. You are getting a distribution. You are having more number of samples that you are defining by a Gaussian distribution. But in case if it going to follow through this, then whole thing would be your stochastic in nature. So in that case, you can't have the gradient flows from your start to end. That means that you can't perform your objectives. For that matter, because gradient cannot operate through a stochastic variables or parameter. So when the encoder learns, it learns its mean and the standard deviation as a feature. So to isolate that, it has a reparameterization tree that is a parameter we may say epsilon. Actually, that parameter is getting sampled from a normal distribution 0 and 1, and that is getting multiplied with the sigma. So that's the way when the whole thing is done. So this actual parameters through which these gradients are getting flowed, that is getting isolated from the stochastic nature of the whole thing. So that is called the reparameterization. You can give a search and you can understand there are a lot of, I think, things are there. So coming to your point that when you are collecting the data and that you are feeding to any variational autoencoder model, if you take it out from the GTAB and on all the things. So in that case, it is anyway, people are considering that. If you see the code, then I don't know, I have just in my code it was there. Anyway, so if you see this, then you are going to understand that how it is going to work. So if you capture the sensor data and then you feed it into any kind of variational autoencoder model, and if you write by your own, then you anyway have to take care of that reparameterization trick part. It is not related with any different types of sensor data and all, which is important that Depending on the complexity of your data, you may have to change your encoder. Like say for example that if I have a sensor data for accelerometer and if I have a sensor data for EEG, I cannot expect that both of them are going to have the same kind of architecture, even though both of them are time series data. But it is not, because EEG data is very much complex in nature. Or let's say for example the way I'm going to process the data, for example that I'm going to generate the data for some kind of sequential process, some kind of historical data. With that historical data, maybe for example that my location visits, so I have a lot of visits and I have a lot of history that I have to take into account for generating the data for my next time frame. So for that matter, I cannot consider that my encoder to be identical for all. So it is important for that encoder part, which actually encodes the information. This is applicable for any kind of model we are considering. So that is, I think, a part we have to take into account. And the other part I said specifically for the variational autoencoder part, that the this annealing part and all. So we can give attention to how we are train the model and what way we are going to train the model. Now TensorFlow and all the things are very, I think, helpful to modularize your code, modularize your architecture of your code. And similarly, other point we have to very importantly keep in our mind when we generate the data and we give some kind of prior knowledge and all, that time we should focus on how we give the conditions to the model. For the conditional GAN and conditional VAE, both the cases, these two are very important. And nowadays, people are talking about the diffusion model, which is actually adding up the noise and then denoising part. So that's the way I think the main crux, that where the complexity is coming up is in your encoder part, and then how you are going to regularize your system, giving your system knowledge while setting up your objectives. I have given you two, three examples. That is also very important. Okay.
Okay, thank you, ma'am.
Any other questions by the participant? Please can you ask.
Ma'am, I have a question.
Yeah, sure.
So, how is using domain specific knowledge and custom loss functions
Yeah.
for this data generated neural networks in sensor while sensing the data synthesis? How is it different from the physics based rules in physics informed neural networks to form the physical systems? Both are more or less doing the same thing. How do we say both are doing a different job on the same?
Claimed that both of them are doing different job. If you are using physics informed neural network by using some generative models, and you are using physics informed neural network, which is a deep learning based generative model to generate the data, then that physics information is your domain knowledge. I have never said that, and I do not mention it also.
No, I'm not I'm asking you like what is the major differences we can find between these two?
All right.
Uh,
So, see, the physics informed neural network, when you encode the physics rule, you have some different objectives, right? You may not have
yeah.
the objective to do the data generation, data synthesis. If you do the synthesization part, and this data synthesization part, you are embedding your knowledge. I have given two applications and two ways to do it. One, I mentioned that you can condition in a probabilistic fashion, you can use a conditional probability to apply the domain knowledge. And that is getting factored when you do the learning. Secondly, I said that you have to understand that when you are going from one domain to other domain, how your knowledge what features are going to be affected and how it is getting changed. So that way you can have a domain adaptable feature loss. So now this domain adaptable feature loss could be based upon on some physics informations. Like the way I have shown you that in the progressive
Yes,
phase,
ma'am.
it's completely physics-based knowledge. It solely depends on that the crust is when the fault severity changes, how your stiffness changes. And the stiffness is getting computed with the different physics-based parameter and physics-based equations. Once you've done that, you come up to a point that how this GRMS frequency is getting affected and what would be the factor when we go to states 1 to state 2 and state 3. So with that, we are using a regularizer or constraining our learning process towards it. So this is a sort of physics guidance we are taking. This is
Okay, ma'am.
a physics guidance. Now physics informed, let's say that you could have a neural network where your activation units performs the way the physics particular law works. You can have a sigmoid or tanh or maybe a RALU you are making in a fashion that you are going in one state you are going only 0, then for the next state you are going 1, and that those are getting added up. So you could imagine that your encoder is getting formed in a way so that in every stages they are going to perform some of the physics based equations uh, in from the next one layer to the next layer. So the exam, and then if you do this data generations, and then you have to come to this encoder process, or in case of GAN you have this your instead of the encoder and decoder you have to have this generator. Through the generator you are going to do that constructor and generator, you have to have that. So there is the differences are basically in our mind the way we will build. In physics informed neural network we mainly focus means in one scenario, in one genre, people are looking into that the physics are getting done by the different neural network units.
Yes, ma'am.
When we are doing this adaptation, we are saying adaptation that externally this knowledge are getting fed into this model. That could be done in different format. And in one subtle point, we can say that physics informed neural network as a data generator that is also going to do some kind of domain adaptation. You
Yes,
understand?
ma'am. Yes, ma'am. Yes, ma'am.
Okay. Thank you.
Yes, ma'am. Thank you,
Yes.
ma'am.
So it is 7:35. I'm eating up 5 minutes of time or no? 7:29. Yeah.
And any speaker still, any participant would like to ask any question again? All right. If in case there is no other question, you may reach out to us, and we can try to pass your queries to the
Yes,
speaker.
yes. Thank
Yeah,
you. And I'm
and
really extremely sorry for that, that
in the
screen
initial,
sharing part, because I always
yeah.
value the time. And since
You have already mailed us regarding that, but unfortunately we are unable to change the
that's
link.
it. But anyway, that 7:30 it is, but you are anyway getting bored for first 15 minutes. So as for that, I'm really sorry for that.
No problem. It's
Okay.
part of the thing. So then let us thanks again, Madam Soma Bandyopadhyay, for sharing her knowledge and excellent talk, and actually basically I mean giving a valuable time to us to so to
Okay, thank you very much. Thank you very much for listening and coming and joining to this. And I think I will meet with you all again. With that,
yeah,
I'm
definitely.
just finishing. Thank you very much.
Thank you,
Okay,
madam. Thank you.
thank you. Bye.
Bye, madam.
Okay, I'm just dropping out now. Okay.
Sure, yes, madam.
Thank you. Thank you all.
Thank you, madam. Okay, so once again, welcome back to the to all participants for this session. I mean, we have Dr. M. Saravanan as guest speaker. So before he start his talk, let me take a privilege to introduce him. Dr. M. Saravanan is as principal researcher, ERICSSON Research, AI/ML Data Sciences, and Quantum Computing Saravanan has got MS and PhD degree in computer science and engineering from Indian Institute of Technology, Madras. He has a background in research and development in telecommunication business and other relevant areas with experience of over 20 years. He has been working with Ericsson for past 15 years in global research division and filed many more than 60 patents, published 100 research papers, various international conferences and journals. He has good experience in developing research prototypes relevant to the customer business. His interest in the field of data mining, text mining, information retrieval, mobile social network analysis, IoT and big data analytics, fog computing, neuromorphic and quantum computing. He has guided more than 100 research interns, mentor for PhD scholars for different universities. With this small introduction, I would like to hand over the session to Dr. Saravanan. Last one is I would like to greatly thankful to Dr. Saravanan for accepting today to shift the. I mean, the talk was scheduled for tomorrow. Unfortunately, Professor Sivaram was not able to join because of his health issue, and instantly, Saravanan sir actually agreed to give a talk today. I'm really thankful to you, sir.
Thank you. Thank you for me. Yeah.
Thank you, sir.
Thank you. Thank you for the opportunity, first of all. And it's a great pleasure for me to be a part of this particular FDP program. So I think I will share my screen, and also I cut short my turn off my camera, because otherwise I don't know if you get a good bandwidth. So I will share my screen. Where to share the screen here?
The bottom arrow, sir.
Yeah, bottom arrow.
Up arrow, yeah.
Exactly. So it is window, no? I think, or entire
no.
screen.
Entire screen.
Yeah.
Entire screen. Yeah.
Yes.
Yeah, it's appearing.
Yeah.
Yeah.
So able to see my screen?
Yeah. Yes. Perfect.
Yeah. Okay. So good evening to everybody. Yeah, this is talk related to the sustainable AI. That is the area where now people are looking into that because of the larger developments on the hardware, software, and many areas. Actually, people now look into the way of the sustainable, and not only in the AI, all the different areas. And one of this particular area is called the sustainable AI. This is a little bit a tricky topic actually, because we can interpret this in two different ways. One is how AI introduces sustainability in various areas through automation, improved performance, faster decision making, distributed, federated, edge-based, and many different areas. How we can able to introduce the sustainability. AI will support the creation of, again, a low carbon energy systems with a significant share of a renewable energy and energy efficiency, which are necessary to all the climate changes and enhance the ecological health. Because the data center, we have to consider on the data centers. A study by Google and the Boston Consulting Group suggested that artificial intelligence might mitigate the greenhouse gas emissions globally by 5 to 10%. So moreover, AI role in accelerating the development of sustainability solution is multifaceted, and also it application spans across the many areas such as the renewable, low carbon material, climate resilient architecture towards smart cities, smart manufacturing, and smart agriculture, wherever you use AI. Okay. But this is the way of the AI introduces sustainability. Second aspect is AI sustainability. That is, the AI algorithms consume huge memory and exponential requirement of the power to process the data. After the introduction of LLM generative AI models, all the CPUs and GPUs are overloaded. You know that almost it is crying now, because all the data centers are completely compact. And then, is it a way to save some energy or a power at the same time without compromise the performance? That will be a very important questions related to the AI sustainability. So this type of energy efficient algorithms are sort of the requirement for many different fields. especially in telecom, which we are working on that area. That need is abundance, because huge network. Example, you know about that number of telecom, mobile network connections. Okay, billions there actually. So all those things, when we are connecting it on all those things with energy efficient algorithms, it's very must in RAN applications, many other areas. Actually, I'll start with one of our FCTO's view on energy efficient networks. Innovations that contribute to the emergence of more energy efficient networks are of a growing interest to the communication service provider around the globe for economic, sustainability, and regulatory reasons. We are in ERICSSON, we are already doing an extensive experience of network operations and optimization has been invaluable. Our research efforts to identify opportunities to minimize energy consumption in a mobile network while maintaining the consistently high quality of excellence, quality of experience or quality of excellence. Despite the many energy efficiency solutions already implemented in mobile networks, energy consumption continues to rise in response to the rapid growth of both network traffic and data volume. So we are doing a lot of energy efficiency gains can be achieved in ML algorithm, but still we need to do a lot more on the higher level of automations. So this itself says that how much effort we put for the building the energy efficient or sustainable AI sustainability related things like energy efficient, which we are talking about. So we move on to the area, it's called neuromorphic computing. Neuromorphic computing, it's a new way of artificial intelligence. It is a method for computer engineering in which elements of computer are modeled after systems in the human brain and nervous system. And another thing is called the brain-inspired computing. In brain-inspired computing, basically we are planning to build a more energy efficient algorithm. You know that human brain is amazingly energy efficient device. In computing term, it can perform equivalent of explop, that is a billion of billion, like 1 followed by 18 zeros, mathematical operations per second with just 20 watts of power. How efficient it is actually. In comparison, one of the most powerful supercomputers in the world, the Oak Ridge Frontier, has recently demonstrated the explop computing, but it needs 1,000,000 times more power, that is 20 megawatts, to pull up this feat with our 20 watts of power which our brain is taking. So the brain's plasticity, that is hardening and softening of nodes in the network neurons, so that the different input trigger in different outputs, is represented by the weights and biases in the deep neural network model, which we are going to see that. So brain-inspired computing ships with energy efficient AI performance. Maybe once it is started, it started the door for utilizing the smaller and more portable devices rather than just having to rely on large infrastructure available in the cloud. So here, one of the very important neural network model, which you are planning to introduce, it's called the spiking neural network model. It's an energy efficient alternative and more similar to the neural neurons. And it is fall into the third generation of the AI. So common approaches to reducing the energy consumption to data mainly exist in improving the underlying hardware while still adhering to the typical one human architecture, which we are using like a CMOS technology. However, a more promising approach lies in the neuromorphic architecture, where the goal is to create biologically inspired computing chips for a machine learning that deviates from the standard one human approach. This biologically inspired approach places data and processing power in the same place, much like how the brain operates, reducing the overhead in moving the data to and from processor for intensive calculation that's done in the typical ML approaches. So it is really a quick paradigm shift where a neuromorphic architecture has been introduced. So an architecture where the memory and the computation are separated by a bus. Okay, that is what the general thing. Both the data for the program at the end as well as the program itself must be transferred from memory to a central processing unit. And interestingly, most of the power and the time consumption arise from the back and forth between the memory and the CPU through one human bottleneck. There has been a great progress in CMOS technology, but still it has resulted in this architecture being significantly more power efficient and faster. But this is again will not be a self-sustaining. So which is evident from the plateau of Moore's law and the slowdown of the Dennett scaling, which we need to know about that. Eventually, this conventional hardware architecture will always be a little bit of problem, because when you are doing the perspective of AI ML, where we need to build intelligent systems, we can observe an untenable difference in both structure and the function from the human brain, which may safely termed as a pinnacle of the intelligence, which we are trying to mimic through computers. That's what the neuromorphic technology and neuromorphic computing. It actually the neuron and synapses as communications are everything intact together. There is no from front and back processing as nothing has been done. All these things in the single neuron, this has already been connected with all the memory together. So what are the benefits is basically like here, it's highly connected and parallel and low power consumption, co-located memory in the processor, which you have seen. It is more on a event-driven processing. So a specific event which is happening, it actually based on the event, the entire neurons can able to fire, and then based on the process, we'll get some specific results. Simple communication between the components. We are going to see how the communication is happening between this particular entire in our brain neuron model. The same similar way will be depicted in the brain-inspired models. Learning in components. Theoretically, neuromorphic computers have a potential to perform complex calculations faster, more efficiently, and a smaller footprint than the one-to-one architecture. So I think this is considered to be the third generation AI. Before that, I think we know that first generation is based on the McClush-Pitts neurons as a computational units. There are also referred to as a perceptrons or the threshold gates. They give rise to a variety of neural network models, such as like a multi-layer perceptrons, also called the threshold circuits, off-field nets, and Boltzmann machines. We know all these things. That is the first generation computer. And the second generation is based on the computational units that apply on activation functions with continuous set of possible output values to a weighted sum of the inputs. That's what actually we are looked into that concept called the sigmoid function, activation functions in the deep neural network model, and many other neural network models. For a biological interpretation, the neural nets from the second generation views the output of a sigmoidal unit as a representation of the current firing rate of the biological neurons. So still, when I say about the brain-inspired, not only the SNN, spiking neural network model, even the neural network models and convolutional neural network model, everything have a little bit effect on the simulate our biological neuron, but structure-wise it is different. But when you wanted to firing the neurons involve these computations are usually below 100 Hz, and in at least 20 to 30 megahertz would be needed to sample the current firing rate of a neuron in the artificial neural network model. And but on the other hand, now we can see a third generation AI where neurons with no neural input do not require any processing, because every neurons are inactive. Only the specific neurons will fire. Not other neurons are inactive neurons do not communicate. So during the learning or interference, most of the neurons are only very few. I'll show that example there. So it's very few neurons when only executed. So inactive neurons have a zero running cost. That's why we can save a lot of power. Okay. So experimental evidence recently suggested that many biological neural networks are the timing of single activation potential or a spikes to encode the information. And it leads to the third generation of the neural network model, which employ the spiking neurons as a computational units. So more knowledge requires a bigger network, but it does not bring proportionally more communication nor computation. So that's why we say even our modern GPU consumes 200 watts, our brain consumes only 20 watts, while having 100 trillion synapses, which worked on that. So the implementations, many models have been implemented related to the neuromorphic system. Some of the models are biologically plausible, biologically inspired, neuron plus other, integrate and fire, and McClush-Pitts. These are all the various biologically inspired models are available to running under the neuromorphic systems. Spiking models have been the popular in spiking neural network model, which are very popular in the neuromorphic implementation. And memoristors help in hardware implementation of the spiking neural network model. It has been already been tried in many of the areas where there are people who have tried with a little bit on the memoristors. We worked on that. not been implementation of the spiking neural network model. I'll come with the applications and we'll go to the more detail on the spiking neural network model, where it can be applied. So maybe I think before going to that, we have to see whether we have to conceptualize that. What are the different applications where I'm going to propose an SNN model could be applied. It's called the image classifications. Example, you know about how to classify the dog and the cat in a very simple image processing tasks. Okay, so this can be very, very, very useful actually. And robotics, we can able to use it actually to be one of the very interesting way of applying it to that for the robotic automation functions. Classification models, we can able to build a lot of classification models and can be very, very useful to the anomaly detection. I'm going to show one of the experiment we performed on the anomaly detections where we can get a marginally better on the SNNs compared to the other neural network model. Other NLP tasks, natural language processing tasks, are very, very important where you can able to try to use NLP based things there. And smart sensors, I'm going to show that this is one experiment which we have performed in the recently concluded Indian Mobile Congress, how the smart sensors are used to communicate and even more energy efficient. And video and sound. So this is another area where we can able to try to use. And another area is medical health sector. It will be very, very useful to process all the ECG, EMG, and all the different data. It can able to process the data. So now we can come into the main topic on ideal spiking neuron, where there are three functional units of the neurons are called the dendrites, axons, and soma. So you can see this actually, this is a dendrite and this is the soma cell body. Here it is attached and then it is connected to the axon and it is connected to the axon terminal. So this is here this terminal connected to the other neurons. Okay. So this is the one interesting architecture of the neuron present in our entire brain structure. The junction between the two different neurons is generally called the synapse. So the sending neuron is referred to as the presynaptic neuron, and the receiving neuron is called the postsynaptic neuron. So the neurons are connected, and same thing like with our our neural network or how our network as general network, human network, or everything, how it can be expanded or communicated together, connected, or a mobile network. So it is same thing similar to that, how the neurons are connected in our brain. So when it is going to fire, like example, the spike, neuron voltage reaches a threshold voltage and emits a spike. Okay, then only it spikes. The particular neuron can spikes. On spike emission, neuron voltage is reset. After the emission of the neuron, voltage is reset to the 1. So spike is transmitted to postsynaptic neuron through axon. So the other neuron can take it up and then function on that. And synapse connects the postsynaptic neuron axon and presynaptic neuron axon and postsynaptic neuron dendrites. When pre and postsynaptic neurons are fired together, synaptic strength is higher. It's called the STDP rule. That is spike timing dependent plasticity rule. It's called the spike dependent plasticity rule. So what is a spiking neural network model? So spiking neural network model is actually a combination of neuroscience and artificial intelligence. Okay. The spiking is the third generation of the neural network model, where we are specialized network topologies that reinvent the entire computational process. Are a typical type of artificial neural networks, but fully mimic the working principles of the human brain and communicate via spikes. We know that artificial neural networks are based on highly simplified brain dynamics, since it is also based on a brain dynamics, and have been used in a powerful computational to solve the complex pattern recognition, function estimation, and classification problems. But throughout the development, ANNs have been evolving towards more powerful and more biologically realistic models. But in these decades, the third generation spiking neural network model have been developed, which comprise of spiking neurons. Information transfer in this neuron model, the information transfer in the biological, like an information transfer in the biological neuron, like how that actually I told you about the synapse, soma, axon terminal, how it is connected. Okay, so we are the precise timing of the spikes or a sequence of the spikes. Addition of the temporal dimension information encoding in SNN yields a new insight into the dynamics of the human brain and the potential to result in a compact representation of the large networks. have a great potential. SNNs having a great potential, solving the complicated time-dependent pattern recognition problem defined by the time series because of their inherent dynamic representation which it is at. Because it is interconnected with the computing elements, neurons and spikes to communicate with each other, and it both on spatial temporal aspects, building whenever the computational models. But spiking makes it smarter and more energy efficient. That's what we are going to see in some of our applications. So you see that the difference between the biological neuron, artificial neuron, and also the spiking neural network model. How this neuron, it is always mimic the entire brain functions, like axon from the neuron, synapse dendrite, and activation function, and output axon takes that image. Okay, but here in artificial neurons, we work with a different way of getting all the weights and then summing up and activation functions by RLU and then output. So we are coming out with the third generation neural network called the spiking neural network model that it more closely mimic the functioning and structure of the human brain. But unlike the predecessor like ANN, where learning is mostly based on some optimization or a statistical measure using biologically realistic models for both learning and the information coding. So here, one of the very important thing which you are going to discuss is concept called the spike trends. You see that how the neurons are spiking. Example, in this particular diagram, you can see this is in a time period of the milliseconds, 200 milliseconds to 700 milliseconds. You can see how they are firing. Not all the things are firing, only very specific things are fired, actually. Neurons are fired. So the neuron signal consists of the short electrical pulses called the action potentials or the spikes of amplitude of 100 millivolts or 1 to 2 milliseconds. A chain of action potential emitted by a single neuron is called a spike train. Okay. The information is carried through the number of spikes and the timing. The minimal distance between two spikes define the absolute refractory period of the neuron. So in this case, we are trying to generate one of our image data sets, and that image data sets, how the neurons are all spreaded like this. How the neurons are spreaded like this, and this is X spikes of the neuron from 0 to 250 milliseconds, like time period. And similarly, when you get an output, final output on a classified things, we get Y spikes from the neuron from T to 0 to in the simulation time. So this shows an example of how the entire things will be not to be considered. Only very few neurons are only firing at the end, which can give the result to our SISIC like image could be classified as either a cat or a dog or whatever it may be. Now we come into the concept called the neuronal dynamics, where without any spike input, neuron is at rest corresponding to the constant membrane potential called the U-rest. Usually it comes around like minus 65 millivolts. After the arrival of a spike, so I told you, whenever there is something which is spike comes, like some information comes, the potential changes and finally decays back into the resting potential. It comes back to the resting potential. If it is a positive change, example, the spike crosses the threshold, the synapse is said to be excitatory, that is depolarization. It is a negative change, it is not crosses, okay? It not crosses the specific membrane potential, then the synapse is said to be inhibitory or called the hyperpolarization. So here we can see a postsynaptic neuron. In this particular example, there are three different diagrams. You can see like Z equals to 1 where it is firing. Okay. So when there are two presynaptic neurons like J equals to 1 and J equals to 2. Presynaptic spikes evolves an excitatory postsynaptic potential called the EPSP. Okay. That can be measured with an electrode as a potential difference called the UIT minus U-rest. U-rest is the starting point. V is only the one which it reaches the somewhere of the threshold level. When we are defining the simplest model of the spiking neuron, we have said that neuron V fires whenever it potential and reaches a certain threshold called a V. This potential PV is the sum so-called the excitatory potential PESP and inhibitory postsynaptic potential called the IPSP, which result from firing of these neurons U that are connected through the synapse to a neuron V. The firing of the presynaptic neuron U at a time S contribute to the potential of the PV at a time T on an amount is modeled by the term which consists of the weight and responsive functions. So here I think the second stage, when you see that when Z is equals to Z equals to 2, that arrives shortly after the spike from neuron Z1 causes a second postsynaptic potential, because it comes to the second postsynaptic potential here, and then it comes back. That adds the first one. So this 1 and 2 executes when the UT reaches the threshold of an V, an action potential is triggered. As a consequence, the membrane potential starts a large positive file select execution. After the pulse, the voltage returns to a value below the resting potential called the spike after potential. So there are different models are there. One of the model which we are going to talk about is called the spike response model, where it considers about the same thing like where the presynaptic neuron J equals to 1 and 2, which both send spikes to a postsynaptic neuron I. When neuron J equals to 1 fires spikes this, and similar to the J equals to fires this, then spikes evokes the postsynaptic potential respectively. The total change will be measured in the way of a sum of the individual PSPs, or a change potential could be measured in this type of a form. So there are, in typical ANN, we know that a neuron produces output from a given input by performing an arithmetic on an input which matrices of the weights biases towards followed by some activation function. However, in SNN, the inputs and the intermediate layer outputs are in the form of spikes, and a biologically inspired mathematical neuron model is called the integrate and fire model, where the incoming input spike signals accumulate potential within the neuron, which upon crossing a threshold potential produces a spike signal. Okay, so the response of the neuron is modeled as a differential equation here. So you can see this similar to our brain how it does. Here the integrate and fire model also execute a synapse, and then the same thing like a Soma, its computational things is happening, and then it produces the final spiking signal. The response of the neuron is modeled as a differential equation here. Some of the popular SNN-based neuron models are IF, leaky integrate and fire. This is IF, integrate and fire. There is another one called the leaky integrate and fire. That is one of the very famous model. And spike response model, which we have seen it, this one, etc. Since SNN model employs spike-based inputs and rely on a biologically modeled neurons, the traditional ANN-based learning rules may not directly apply to SNN model. Some of the popular biologically inspired learning rules are the Ebbian rules, spike timing, dependent plasticity, etc. can be applied to the SNN model. These learning rules are majorly used for unsupervised learning methodology. However, in the recent years, the advances have been made to map ANN models trained using Babcock propagation to the corresponding SNN model, which can be used for the inference purposes. So in this neural model, like a leaky integrate and fire model, we trained like a 784 input neurons. Like example, we are doing an image processing. 8, we wanted to take a decision on image. We wanted to say this is an 8. So biologically plausible STTP algorithm can be run it here. And then if you can see, there is a image to spike encoding is happened here. And these are all called the spikes, time-based. So here the LF model used as the best towards the computational efficiency and capability of capturing the essential features of the information processing of our brain nervous system. The model consists of one first-order linear differential equation. I think we have shown it actually, first-order linear differential equation that defines the dynamics of the membrane potential and threshold condition that determines the generation of the final spikes. So I think when we talked about the concept called its scaling efficiency is very, very efficient. No? So you see here, this entire process of transferring, it takes about only 7.4% of the nodes were active on an average. Most of the gain is due to the effective neural inhibition. As the size of network increased 4 times and accuracy improved, but the network activity did not increase proportionally. So we are not. That is why it is more energy efficient. So we are see that very less number of the spikes are only fired, and even though there is increasing the number of network sizes going to increase like 25 neurons to 100 neurons, still we are seeing that nodes very minimal nodes which are active, which can only use it for the way of the processing the and presenting the result. So there are different SNN models are being trained for a learning purpose. It's called the STTP learning, one which we have seen, unsupervised local learning, but limited accuracy and shallow networks. There is a stochastic STTP learning. It is based on Hebbian potentiation model, but it high memory efficiency, but it limited accuracy. It's not that much even it comes near or very close to the ANN. There is another one which people are using it called ANN SNN conversion. Like you can build the model on ANN and convert them into an SNN, and equivalently we can able to train. This is having an incurs an higher inference latency, and other things is like a back propagation model. Like since basically SNN doesn't have it's more on a big feed forward model. It doesn't follow anything on a back propagation, but we can able to use a back propagation model called the surrogate back propagation model. When you use this type of a model, we can see the accuracy is very competitive, and higher training effort is one of the only a problem, but otherwise the accuracy is very good. And we are going to see some of the model which we have performed using the surrogate back propagation on our one of the network anomaly detection model, which we see that it's almost bar with the NN models, neural network models. Okay, so we have seen different models now, but when one of the questions which you come into a mind is how the data has been converted into a spike. So what is the information contained in such a spatial temporal pattern of the pulses? What is the code used by the neurons to transmit that information? You say spikes, but how the spikes are converted from the numeric data or a text data or image data or all this thing. How might other neurons decode the signal? Okay, so there are different popular theories of neuron encodes are available. We are going to see rate code and spike code. There are 4 popular theories are there: rate coding, temporal coding, phase coding, and burst coding. Okay, neuronal coding explains the information transmission between the neurons, where the rate coding is one of the mostly used. We also use rate coding only effectively on our neural network building the spiking neural network models. The scheme considers each input pixel as a firing rate and converts the pixel intensity into the Poisson spike train with a firing rate, but it ignores the spiking time in events. So other time based on that things will not be ignored. Whenever there is any firing is happened on a Poisson spike train, it can consider that. Another model is called the time to first spike code. It's called the temporal coding model. We encode the information for fast responses within a few milliseconds by using the first spikes, but the larger input pixel, the more information it carries and the earlier it emits a spike. So rate encoding is one of the rate encoding and the this is one of the very important phase encoding or the important methodology could be used to try. When you say rate coding or rate encoding, there are 3 different methods to averaging procedures will be there on the rate as a spike count. Example, when you say rate, average over time as a single neuron, single run is happened. It averages the entire time with finding out the spike count. And when there are multiple runs are happened, okay, average over all the several runs, and we can create the spike density. And as a population activity where there are multiple neurons, okay, like n neurons, several neurons, but that is happening on a single run. So it created the average pool of equivalent neurons. So this is the way the rate code can be efficiently worked to convert their data and then to a spikes, and then we can able to sending it to the neuronal computational models. I think I can give 2 minutes or 5 minutes for any, just a second, I think I'll come back before going to the next actually. you have any questions on this? Because now I introduces the spiking neural network model. This is one of the third generation AI model, and how it mimics our brain, how it functions, how it encodes, how it creates the model, and how the results are it's emitting as a final spike or a symbol, which can be used as a class, either classification model as a class label or a prediction model as a prediction value as a proportionally the percentage of the value, something like that. Or even it can be a combination of reinforcement learning. We can able to work with the SNN and RL model to combine together. It can able to compensate for a better way of the prediction. So if you have any questions, you can ask me in this thing. Then I will go into the how the models are prepared and what are the experiments we performed. I will take it to the next.
So there is a question in the chat box.
Oh, okay. Just a second. Yeah. Yeah. I think already it will be used. A lot of SNN models are already been started, being used and executing various applications. But still, we don't get a proper neuromorphic hardware. But still, it can be worked on a conventional machines. It can be compared with the ANN models. That's possible now, actually.
Hello, sir. Sorry, I didn't see that my mic was turned on.
No problem.
Thing is, if this spiking model, how relevant is this in mobile applications? We see today that there is so much of radiation being generated, or they say usage of mobile. The more you use the mobile, it gets heated up or something like this. So how are we going to apply, how can we apply this particular model? Like, we are using electronic devices and electric devices more and more.
Yeah, but this is not very particular about the reducing the heat and other aspects. Maybe it will become in future.
Mm-hmm.
The SNN model can be run on your mobile phone. But we are going to talk more for basically for how the computational efficiency when you're building a model for the various applications related to the like anomaly detections or a many other prediction model, throughput prediction model, or many things. When you wanted to apply instead of the ML models, instead of the neural network model, when you wanted to apply this type of SNN model, how efficient, how this saves a lot of energy, okay, in a computational time. That is
So
what actually we are going to discuss here.
yes, sir. So my question is, there now that this model is being developed, so there is a scope that we can use this particular model in computing the energy, how much of energy or radiation is being generated in electronic devices, and we can actually get those down.
Yeah, radiation is another part actually. Energy in the sense the computational, how the machine consumes the energy for performing your calculations or performing your algorithms. That is the one part. Second is number of memory usage, how much memory is used for this computational effects. So this is what to be considered here as an energy efficiency in building the models. So that's why we come with the brain inspired AI model, because I told you the brain consumes only 20 watts of the power.
Yes.
So similar to that, how our algorithm consumes very, very less power. So it will not be, maybe later if it is applied, it is run under your mobile phone, it will not be heated much faster because it is not consumes more energy. That all come into the in future. But at present, we are looking into the data centers and many different things where it consumes huge energy. So is it possible by running this type of the models, brain inspired models, can reduce the power energy? That is what actually we are looking into that.
Thank you, sir.
Yeah. If no other questions, can I continue, sir? Yeah.
Good evening, sir. One small question, sir.
Yeah, please, madam, go ahead.
So this backpropagation algorithm, basically, suppose if I will try to optimize the weights of a neural network,
Yes.
chances are there it will stuck at the local minima, and there are certain limitations. No, can we use some global optimization algorithms, sir, to hybridize with the ANN to rectify this?
Yeah. It's possible actually. We can try many different. Now I think it is only into the trial basis now, because this type of algorithms are now only possibly they're trying the various combinations, because since we don't know about which encoding schemes could be used for any specific application, where we'll get a good marginal difference, which neuronal models can be used, whether LIF or IF, or all are still will be a very challenging things here. Still, there is a lot of research which going on to finding out whether we need to use this type of backpropagation, surrogate backpropagations algorithm, which are very very useful to effectively improve the accuracy part. Because when you use a feed forward only, I think the accuracy will be a little bit questionable. So when you use a backpropagation and I think we can able to try to improve your accuracy level more comparatively. That is what actually we are looking into that.
Okay, sir. Okay, thank you.
I'll show you all the examples with the results also. I can able to discuss now.
Yes, sir. Thank you.
Thanks. Okay. I'll go into my camera off mode, because otherwise we get into that. So again, I have to go for the sharing mode. So able to see my screen again?
Yeah, yes.
Yes. Okay, good. So there are various methods which I told. The third one I told you is the ANN to SNN conversion. This is called the deep SNN conversion model. It involves mapping the trained ANN parameters into the corresponding SNN parameters combination. The conversion methodology ensures that resulting SNN behavior matches the ANN behavior according to some spike-based information encoding model. So it more or less similar, but it is having an inherent features or inherent behavior of the SNNs using the different information encoding model and everything. So one of the very important framework, if you wanted to try, is called the NengoDB. Nengo is basically NengoDB. It is not DL. NengoDB models. It's a simulator which you can able to prepare your ANN model, and using the NengoDB we can able to convert them into an SNN, and then we can able to run your SNN models. Okay, so this is possible. So now actually we have actually experimented many of our SNN based model that be more suitable for the telecom data, which are predominantly time series in nature. But due to SNN's inherent ability to consider the temporal aspects in data, we believe that SNN architecture can handle the varied and dynamic telecom data much more suitably and efficiently than the artificial neural network. So because of this, there are a lot of comparisons are there. Like when we wanted to do the ANN, the training cost is about 3 million to 30 million in the state of art. One of the expenditures incurred is almost reach about 500 million by 2030. And it can also produce about 626,000 pounds of carbon dioxide, which is equivalent to the 5 automobiles worth of emissions over the lifetime. So all these things are bit questionable. So that's why we are thinking to use a spiking neural network model. We have first initially tried these models with various things. One of the things is called, I think people would have used on reinforcement learning. Should aware of this. That actually in an ML machine learning models, there are supervised, unsupervised, and semi-supervised, or most probably it is called the RL algorithm. It's called the reinforcement algorithm. Reinforcement algorithm can work with more on exploratory on exponential way actually. Okay, so there are different way it can perform. One is called the single agent model. Another one is called the multi-agent model. Okay, so here what we done is we employed the deep Q learning and experiments are replayed to solve the task both cart pole and the mountain. These are the two environment, where the cart pole environment and the mountain corn environment. I think people have talked about the global maxima. Here actually this is just the global maximum. So the architecture for the ANN and SNN model used in the deep Q network of both the cart pole and the mountain car is simply a two-layer linear RULU model we have used. Both these networks consider the mean squared error as the last function and also using the Adam optimizer. For the multi-agent environment, we have used the RWAR, randomware is one of the, I think all the tools are available in OpenAI, like an RL models. These tools are available in OpenAI. So SMAC, we used a value decomposition network algorithm where value functions of all the agents are implemented using the neural network. So here we're using a deep SQN model, like example, when you are using the neural networks as the value functions. These neural networks are updated based on the collective rewards rather than the individual rewards to improve the collaboration in general RL model. Here it's using the collective rewards and then you can able to execute as a value function. So it has been implemented by converting the ANN into SNN conversion using the PyTorch spiking and Keras spiking model. So we use both provides a tool to train and run SNN models directly within the PyTorch and Keras frameworks. Convert the activation functions in ANN models to the spiking equivalent ones in the SNN models. And be using the temporal aspects of the data model to model the data. The final layer to get a single dimensional output because we wanted to predict whether we need to go ahead or a final reward value or something. Temperature, okay, we have taken an average across the time dimension. That's why we can get a single dimensional output. Such converted models are spiking activation functions in the forward pass, and on-spiking activation function is the backward pass. Now we can see the results here. Actually, what are the results which we have compared with ANN and SNN by running onto the deep RL models? Mean reward for the different models and environments are given in a table here. We can see comparatively the mean rewards are better in SNN, even in the same conventional computer which we performed, but not on the dedicated neuromorphic hardware. Mountain car, randomware, star graph, we can see almost there is a small or little bit of good improvements will be in the mean reward. And also we can see the reward and episode plot, which we can see here, where ANN and deep RL are almost implemented in the carpool or little bit similar. And similarly for that, when the reward and episode plans for method on the mountain car, we can see there are a lot of spikes here. Even the SNN model are little exploratory, we can see very clear spikes and then can reach the maximum much faster in a lesser episodes. Similarly for the randomware environment, and also we have done it for the other environment on the star graph environment. So even though this could be goes down with little bit on the things in a new episodes thing, we have seen there are little bit more improvements here. We can see one more results here. So here we are getting it a little bit more down. So we wanted to try to get into the performance of an ANN. We have to try to tune the parameter. There are different parameters or hyperparameters there in SNN model. One is called the time step. Time step is a TT. TT we can able to give a value. When, for example, when the TT is 0.1 milliseconds, this is the one. When you give TT is 0.1 millisecond, there are a lot of spikes. And 1 millisecond it may vary and reaches the very faster. And 5 milliseconds, again, it should be some drops there. So we have to choose 1 milliseconds is the best. Or we can use hyperparameter tuning for the carpool environment for the TD equals to 10 milliseconds. And when you use TD equals to 20 milliseconds, we can see. So this is the way you can able to tune your hyperparameter and try to see the differences, and you can able to get a much better. For a single agent carpool environment, when you increasing the time TD improves the trained RL model, it converts to the higher reward value. This you can see it reaches to the higher reward value. However, the important seems to be the stop after a limit. We can observe the TD 20 millisecond performs worse than the 20 milliseconds because it drops here. However, for a single agent mountain car environment, we observe how increasing the time step TD worsens the model. No? When you increases that, it automatically worsens. So TD increases, the model converges to the lower reward value and it increases. In the multi-agent randomware environment, we can observe that low time step values do not provide a good results. The environment works best at time step close to TD equals to 10 milliseconds. Like TD equals to 10 millisecond. I think this diagram is 1 millisecond and 25 milliseconds are there. It's not there. The multi-star environment seems to favor a small step close to 1 milliseconds and sufficiently lower higher time steps does not provide the good results. So this is what the findings now. So this is one of the very, very difficult process in SNN to tune your parameter to reach and get the value. But still we have a very good outcomes. We have seen it here. So compared to this particular work on a oral random reinforcement learning, working under the OpenAI platforms or the single agent and multi-agent environment, we can see that the environment is a complex, but it requires precise and frequent action. We need to choose a larger TD value for certain cases. There is, since actions are so frequent, we need to ensure spikes are measured at a larger time interval to present noisy outputs. But when you say simpler environment, we don't want to take a frequent actions. We can have a smaller DD value as it won't contribute to the noise. So possible reason why SNN-based model outperform ANN-based model in terms of the convergence speed and mean reward could be due to the encoding method of the SNN models. So we are using the rate code encoding methods here. Inputs over time, in the model can view the same input represented in the multiple times over time. So representation to learn from. And we are using a hyperparameter can perform better than the corresponding ANN implementation. And tuning of an hyperparameter to understand the importance of the proper hyperparameter choose for the different types of the model. So SNN-based implementation on a single edge provide much faster convergence to higher reward value in comparison to the ANN implementation. A similar but limited implement can also observe from the SNN implement on a multi-agent environment. This is the first one. Okay, this we already submitted the paper has been available on the net. Maybe I can share the paper. This is the second work. This is basically related to the network digital twin to improve the quality of service performance in the communication network. Okay, so in the communication networks, generally we are representing this in the way of a graph neural network. These are the neural networks that are adopted to leverage the structure and properties of the graph. It transforms the formatted graph data in an input into a vector of the numerical data that captures the information regarding the nodes and the relations called the graph embedding. This is called the graph embedding. Graph embeddings are generally by combining the feature information through the neighbor nodes through the processes called the message passing, which enables the GNN model continuously update the embeddings. GNN models results in accurate predictions, inherent graph structure of the network to further improve structure of the network. So here in this particular example, we try to use 4 different ensembling methods. When we choose the weights, equal weights, weights obtained using grid search, weights obtained through using oral method, weights obtained from the linear model. There are 4 different things which we are trying to use it here. So they are oral-based ensemble methods actually consisting of, since it is following the oral methodology on a learning, it has the states, actions, and rewards. So here, how do you define this? States as a prediction error obtained from the current time instant. Actions are the choice of the weight for the individual models, and reward is a ratio of the prediction error obtained between the 2 instances. So that is the way we are tuning our oral-based model into this particular scenario of the SNN. Here, the choice of the weights is dynamic. The weights can vary, change every time step of the execution depending on the reward obtained. So we have done an implementation like when we first implement the GNN-based implementation by using the RootNet is a GNN that estimates per square distribution performance matrix, delay, jitter, loss, and everything will be considered in this particular scenario. And we can able to ensemble to make the prediction on the mean source destination delays. And the distribution of the delay values was different. So we are predicting the delay values in an optimal approach, not possible. So we predict the queue occupancy through our GNN model and calculated the GNN value. So here you see this type of an architecture where we are getting the link features and flow features, traffic, packets, and all these things putting into the GNN model and embedded link query and then a delay calculation. Similarly, the another GNN model can be done and then go to the ensemble technique. We can get the final delay part will be calculated here. So here we have done an SNN-based deep oral models for the different environments implemented by converting the corresponding ANN SNN-based model into spike neural network using ANN to ASNN converter. Samely what we have done it for the same thing like PyTorch and Keras spiking. Here, Keras spiking methodology are used. In the final layer, we get a single dimensional output similar to that. And such converted model use spiking activation functions in the forward pass and non-spiking activation functions in the backward points. So here the dataset we have used is actually the datasets available in the Graph Neural Network Challenge 2021, creating the scalable network digital twin model performance datasets. It's generated by HomeNet++, a discrete packet level simulator. So each of the generated sample is defined by network topology, routing configuration, and source destination traffic metrics, and which are labeled with the network performance metrics such as per source destination performance and port statistics. This is the way this final performance metrics are evaluated. So here our objective is to create a scalable network digital twin. The topology size of the training sites are vary. We have simulated the topologies of 25, 30, 40, 45, and 50 nodes. And we have sample simulated to 52 and 300. In the evaluation, we evaluated scalability of the proposed model based on the mean delays and source destination path with the two different metrics. The metric considered here, mean absolute percentage error, map, is consisting of that. So the model with the lower map score is considered to be the better solution. So we done again results and analysis. We present the comparison between ANN and SNN-based GNN model. The map for the two models for the M sample for the are given here, like a valid map and the single map. And we can see there are a lot of difference in epochs on the performance of GNN model, GNN plus SNN based models, and performance on a test set which we tested with the map GNN model is 7.3. This is lower GNN model, but with 4 different ensemble methods we have tried. So we are giving it in an averaging method 1.53, linear regression 5 point, grid search is 1 point, and oral method is 4. And then we compared GNN plus SNN models on the different ensemble model. We'll try to get it actually like 2.97, 9.8, and 1.9 and 3.3. So oral based weighting technique it's given below, like each reward the plots for traditional GNN model, and this is GNN plus SNN model. It reaches the top, even though this reaches the top in earlier, this reaches more than that actually. So results show ANN models are comparatively better than the corresponding SNN converted model. But however, so that's what actually this result shows. But however, GNN plus model fairly match with the performance model in the test datasets. And when we compare it, we can see that grid search method works much best for both the models. This can be attributed to the fact that grid search is an exhaustive search algorithm. And we are also done with a number of models that ensamples the grid searches to test larger number of weighting combinations. And oral-based sample in the test datasets, entire dataset whole, generalize well, but limited training on the validation datasets. From the rewards over episode 2, it is evident the reward value is increasing with every new episode, and we have a limited number of the episodes in our figure as efficiently captures our agent learning behavior. So hence we can address this to improve the QoS performance in the communications slowly on that part. Okay, again, I think I wanted to. So any more questions here? I'll go into the next is mostly on energy efficient comparison and how to build an energy efficient algorithm. Even though I just explained about how the SNNs, what are the difficulties in SNN models, now I'm going to say how it could be more energy efficient. We're comparing with the energy efficient scales. That will be in my next phase. Any questions here? There is no questions I can able to, because we have limited time. Okay. So, able to see my screen again?
Yes, sir.
Oh, thank you, sir. So energy efficiency in a brain-inspired AI model. We are coming to the sustainability part here. Even though we are given a big introduction, this we are coming to the sustainable part here. So energy efficiency computations are generally done in this way. Like energy for ANN will be based on the number of plops in the health layer, which needs more on accumulation operation, and FLLA is the number of plops this health layer which needs the MAC operations, EMAC operations. SNN again, it leads to again like EMAC accumulation and the MAC operations. So estimate the computation energy, we apply by 45 NN CMOS process at 0.9 volts, where this EAC, that accumulation operation, takes about only 0.9 joules, while it takes about for the multiplication operation 3.6 joules for a 32-bit integer representation. So depending upon the encoder type, the energy computation for SNN might differ. Example, if it's a red code or it is used for temporal code, it will be a little bit effective. But the MAC operation will come into the place only in the first layer alone. And if any other encoder is present, the SNN model will contain only SC operation in the layer. So that is why we can see that only the first layer, the remaining layer only in the accumulation, like AC operations. So that's why it will be more faster. I think we know about these things like flops. Flops is nothing but a floating point operation per second. It's a metric used to measure the computational performance of the hardware or algorithm, particularly in machine learning and deep learning. It quantifies the number of floating point arithmetic operations like addition and multiplication that system or a model can perform in 1 second. Flops evaluates how effectively a system utilizes its theoretical maximum computational power to perform this operation, which are crucial in fields like high computational precision, scientific computing, and XR. It's a critical metric in assessing the computational proofs and for systems ranging from personal computer to the supercomputer. Is a single run is sum of all the arithmetic operations involving the floating point numbers, addition, multiplication, and all the thing. Accumulate operations refers to the processing of summing value. It takes very minimal flops. With the multiplication involved, an accumulation operation involves adding a floating point integer value without proceeding multiplication. SNNs that mightly involve summing incoming spike signals to update the membrane potential of a neurons. Where MAC operation involves multiply two numbers and then adding the product to an accumulator. So it extensively in the matrix multiplications, in convolutions, but in linear algebra computations in ANN will be taken. So here in our energy calculations, by taking the ratio between the model which takes the highest energy and other models. There are key components in flop efficiency, floating point operation, which we discussed, theoretical peak performances, where in the different systems per second, usually measured in the flops, where it can vary like a giga and teraflops. Actual performances, many floating operations are being executed per second under the specific workload. Benefits are enhanced computational performances, energy efficiency will be calculated, improved research and development, competitive advantages. We can able to talk about the different algorithms. So we talked about one is called the spiking time dependent plasticity STDP models. Okay, these are basically unsupervised learning model, which takes the input on a matrix and then it can matrix phi t and then coding neurons, and it calculates the final recurrent weight by using the error neurons, and then it can calculate the distance. Where here it will perform the presynaptic and postsynaptic spike, and postsynaptic spike versus the presynaptic. This synapse is weakened when there is called the long-term depression. So energy efficiency and biologically plausibility, it's an advantages. Increased sparsity can be slower to, but limitations are it can be slow to never even converged complex. No backpropagation, only beat forward. That is why actually we are planning to use a methodology called the surrogate backpropagation. Here the training method designed to overcome the non-differentiability of the spikes, SNNs. It replaces the non-differentiable spike activation function with the differentiable surrogate gradient provocation function, error backward propagation function. Use gradient based, it is not RLU, sorry, this is not probably there. Use gradient based optimization. Update weight loss based on loss gradient. And efficiency is like advantages is efficient for a supervised learning task. This is more on a supervised learning task. Scalable to deep architecture and give competitive advantage. But limitations are higher computations. It takes more when there are huge networks there, and high spiking rates may lack biological possibility in certain stages, but not on all cases. So we done it with the one of the data set which were taken from the Gaggle. It's called the network anomaly data sets. This is network intrusion data sets, where it could be defined as a sequence of TCP packets exchanged between the source and target IP. So data flows under the specific protocol for a fixed time duration. There are about totally 41 features are extracted, 38 quantitative, 3 is qualitative, and both from normal and general attack data. Each connection is classified as either a normal or an anonymous. It's a binary classification, legitimate traffic or malicious traffic. So when we compared this thing with performing it on an ANN and SNN model, ANN reached an accuracy of 98.6 accuracy, while SNN reached 98.01 energy efficient at the same time. But computational complexity is AC takes about, accumulation takes SNN 4.7, but computational complexity MAC is 1.0. That's what, and ANN AC is 1.0, MAC is 4.93. So energy consumed by MAC operation is 4.96, and energy consumed by AC operation is 0.9. So when you do this calculation on energy efficiency, you can try to find out. We are using the Python encoder here. I told you that encoder also play a part in the calculating that energy efficiency. We have used the Python encoder here. It reads only AC operation. And SSN is a similar architecture, while CNN is a different architecture to match the accuracy weather model. So when you see that number of flops is very less comparatively, energy consumed is also less, almost like 10 times compared to that's what actually 16 times energy efficient than the CNN, and almost like 12 times or 10 times faster efficiency than the ANN model on energy efficiency. Accuracy is always more. It is not very less, actually. It is comparatively better, comparatively compared to that. So we also tried with another interesting data sets called the 6-class emotion text classification natural language processing data sets, where actually we've seen that a labeled text test emotional classification task. There are 6 classes: anger, disgust, fear, happiness, sadness, surprise. Sentence level text is being taken. Single emotion level percentage. We have used the bird embeddings used for embedding the data set, which turns the embedded vector of each sentence to the shape. SNN is more prone to imbalanced data, so we are using the oversampling of that is applied to that. We are trying a different sampling techniques here for addressing this imbalanced data. One is data augmentation. Data augmentation also one more method we are trying. The training set has 18,124 data points. So when you see that testing data sets where ANN accuracy 0.53 because it's a 6th, remember it is 6 class, it's a multi-class label classification. And loss is 2.44. LSTM is a sequence model, and it is really a very good model for the sequence to sequence operations. It is giving 0.57 accuracy. And SNN is almost very close to the LSTM, but loss is very less. That is why actually we perform this type of, you can see this model also like accuracy and model accuracy comparisons with the different epochs. We have done it for that. Okay. All this testing accuracy, the accuracy of all the 3 models seems to be similar, performing slightly better than SNN at the least loss value. So again, we have compared the energy efficiency on the emotional text classification, where we can see LSTM has a multiple gates. Its flops execute set of ANN and hence more energy consumed by it. SNN gives comparable performance to ANN, and models of performance are not good enough for consideration. This comparison just showcased the energy efficiency component of the SNN. So it is almost like 64 times better than the LSTM because it is having a multiple gates. So number of operations are more. And SNN it is almost like 7 times here, 7 or 8 times, 8 or no, more be better than 9 times here actually compared to the ANN. So again, we also done a comparison with one more model that is called the power consumption of SNN, ANN, LSTM, but the number of hidden neurons on the SHT data set. SHT data set is a spike-based speech data set, which transformed from the audio recordings using an artificial ear model. It consists of 10 English and 10 German spoken digits with a total number of 10,420 samples. Okay, so this is another data set where you can see the BiLSTM is also been used, where we can see that with the W equals to 1 megahertz, the power consumption by STM increases approximately an order of 2. Lighted consumption is attributed to the transmission of the substantial amount of intermediate data here. But we can see the power consumption of ANN increases rapidly with the N here actually. But because I think we know that the Shannon's formula, the transmit power needs to scale exponentially with N. According to, in contrast, SNN is more energy efficient, because you can see it here, more energy efficient. And also because it only produces the data when neurons fire, and the number of firing neurons does not scale linear with N. Consequently, SNN's higher energy efficient computational framework holding promise to empower the broader range of applications for the concept, like in future for the edge intelligence and other thing. Okay. So another thing is sequence recognition and time-based data processing are particularly advantageous for SNN. And one of the things is basically like ANNs, including those employed in LLMs, often need to assistance additional mechanism like recurrent neural networks for the long short-term memory units. But SNNs inherently include only the fundamental part of the computation. It can accurately represent the dynamics of the language, whatever the representation, music, or other time-dependent phenomena, thanks to the temporal dimension, like spatio-temporal dimension is one of the very important feature of the SNN model. So again, it natural language processing architectures, which also could be a very important one, because it is more time-consuming. These are power-hungry in traditional deep learning architecture. That's why it consumes very huge power in LLM models when they're in their data centers and other things. When the type of ChatGPT LLMs are run, it takes huge power, huge energy efficiency. So the idea is whether can we use spiking neural network model in the NLP process to save a compute thing. So here you can see how that pin input text embedding, in text go to the spike hour embedding model. Spike train is going into the NN architecture, where we are getting the weight updates. Then energy model has been built, we'll compute the energy. So there are also, we are comparing with the different layers used. We can see that here, layer 0, layer 1, layer 2, layer and then all layers, where you can compare the ANN, SNN and SNN rate rand. There are two different things. One is a plain SNN and another one is the rate-based random-based operations performed on that. So you can achieve that 32% more energy efficiency during inference, 60% during training compared to the ANN for a sentiment and emotion classification task. So can potentially achieve natural intelligence more abstract models, or at least with higher computational efficiency. These are more like an event-driven models. And plasticity, temporal plasticity, like is the ability of the neural network to quickly and changes prediction in response to a new information, is essential for the adaptability and robustness of the reinforcement learning models or some of the other neural network model. Here, SNN uses spikes to communicate between the neurons, leading to the biological plausible implementation. Here, spikes as an events. So SNNs are inherently event-driven. Suitable processing address event-driven representation of the data. So as a result, SNNs trained with event-driven methods that exhibit the advantage of both training and inference when deployed on ultra-low power neuromorphic hardware when it is implemented in the future. So event-driven algorithms train SNN in event-driven manner. We got precise spike timing as a relevant signal of power pre-synapses for a synapse updating. And when the membrane potential increases linearly around the spike time, this method can successfully calculate the derivative of the spike timing to the membrane potential. So this was actually the knowledge due to the relative mechanism they can use to study the operation. There is a lack of effective training mechanism, which can be inhibitory for some applications, including computer vision tasks. So hardware dependencies are capable of parallel synaptic signal transmission rate update, spiking behavior. ASICs recently been proposed. This is neuromorphic ASICs have been proposed. ACPs have recently proposed, can be used to try out your algorithms. There are some major realizations are there, like a brain scale for a European consortium. Logi is actually Intel's product. It is going to available within another 6 months or 1 year. We're already trying to run our algorithms on this Logi processor. Neurogrid from Stanford University, Rolls from Institute. Spinnaker is available on online. Even you can able to try to run your algorithms on Spinnaker. True North is from IBM. This is again, they are trying to release this model. So recently this is what actually the conclusion of our energy efficiency part and how it could be hardware dependencies and all these things. Recently concluded IMC, Indian Mobile Congress, we have presented this one of in a booth called the Brain Inspired AI. There are a lot of participants were there, and we have presented our idea of the Brain Inspired AI, which consisting of ultra power AI technology for AI for our next level generation of the 6G. AI must be more energy efficient. AI will be AI native. 6G will be AI native. End-to-end prototyping. So future AI must be more energy efficient, where it can have a sparse computations, event-driven, stateful, because generally it is stateless on the other things. This is more on stateful. Sigma delta is a very small delta operations. It can do, it takes them a very small neurons can fire. Neuromorphic computation, low latency interference, like computation by spikes-wise tensors, continuous learning, and all these things. So end-to-end when prototyping is like we have taken a smaller devices, small devices like some amplitude transformer and all these things, and we taken those devices, and then we are trying to do a like a base station. We try to connect it to a base station, like sending that information, like transmitting, and then we are receiving the signals, and by using some way of an embedding decoder, AI channel estimation and equalization, and we are calculating everything in the way of the cloud. So this is the model which we have shown it actually. We are sending actually the small received signals, like small device, like I think I told you that there's a small device. It sends information. This is like an amplitude, like actually it tends the amplitude like subcarrier index. This goes to the spiking neural network model. You see, not all are white. There are a lot of black points here. Okay, so this only very minimal spikes are happening. This activation reaches only about 3%. So 97% it is not, it's energy efficient. And it converts the AI fitted channel model into the subcarrier index. It's almost similar to the equalized symbols which you are generating it. So you are running by shaking your instruments, trying to see how it can. So it takes about 17% when you shake, small modulation or small changes happening into the environment. Even it goes to the 26%, still we are able to save 74% of our energy. But even some cases, it is very ideal cases, it takes about 99% energy be saved. Only 1% will be an activation rate, will be happening into the 10 cases. So neuromorphic compute is energy efficient when it is it's avoiding the one human bottleneck. We are doing an asynchronous processing that neurons fire and process information independently as needed. Sparse activation, and we need a special active hardware. It will be, the performance is very effective, and it consumes very low energy. Other areas like edge intelligence and LLMs are very important things which we need to see energy efficiency. You see the wearable sensors like EEG, ECG, everything connected. When you use a neuromorphic edge computing, we can see the entire health monitoring services can be done on that much faster with energy efficient. It can be used in LLM. Next big thing going to happen in these things is like how this SNN can be plugged into the LLM to save the energy part actually. So there is a one model has been available. It's called the Spike GPT. It's spiking neural network for the language generation, promising alternative for the new generation AI model, generating the power language, more energy efficient. We can decrease dependency on that currently dominate the language generation field. Also offers a huge benefits of the data security and privacy, which is one of the prime concern now. And any language generator on a local device, data inputted to the systems are much more secure here. ChatGPT, where I apply the mathematics behind, requires matrix multiplication, a complexity which is computationally consumes a very huge calculation and very huge energy. When trying to combine the self-attention with SNN, there was similar complexity problem, but technically to feed each data point in a sequence into the NSN model by one, like a one spike in put together, eliminating the need of the big matrix multiplication. It's all in sequence model. It will executed by the one sequence, one by one, and eliminating the need of the matrix multiplication. That itself takes a very good average on the Spike GPT is available on the net, so it can be combined with the LLMs. Can able to work on this. And finally, I can end with this 17th Sustainable Development Goals will be followed by the United Nations in 2030 Universal Call to Action in Poverty, Planet, Ensure 2030 by enjoy the peace and prosperity on the entire world. So they wanted to follow all this sustainable development goals, different sustainable development goals, like no poverty, no hunger, good health, whether we are using AI or not AI, but we need to achieve this sustainable goals in 2030, which make it more feasible, peaceful, and more prosper world. That is what actually the idea of the entire things. Yes, I have completed. I think I have 8 minutes time. Sorry, I rushed it in the end point because I could not able to answer your questions if I missed that. Yeah.
So the participants can answer, can question the, the discussion, something can be done. Anybody is interested to ask something.
So here I started with explaining about the new way of an architecture, then the new models called SNN models, and then how the SNN model will perform, how it encodes, how the model can be formed, and then what are the results when you're running it on a different environment. Then we think about the case that how these models are energy efficient. And for that, I think we run some models and we can prove that it's more 60 times, 40 times more energy efficient than the neural network models. And finally, it can be used in many applications. And even with the LLMs, it can be used in future. So it can save a huge energy on that part. So that's why it's sustainable AI. Any specific questions or any part of my presentation you wanted to get it more cleared or understanding, please feel free to answer. Question me. Is it crystal clear? It's very good.
Hi, sir. It's me. So I would like to get in touch with you about this more of SNN models, and I would like to take my research in this area.
Okay.
So I would like to get in touch with you in future after this presentation too. So can I?
Yeah, m.saravanan@ericsson.com is my mail ID. m.saravanan.
One second, sir. 1 second. m.saravanan at ERICSSON.com. Is this the one, sir?
Yes, madam. I think I also. Yes. You can send a mail to me. Maybe we'll connect and then we'll try to see.
Thank you, sir. Thank you so much.
Yes, yes.
Sir, I have a question.
Please go ahead.
Sir, after the matured neuromorphic hardware or the ecosystem, what will happen to the existing ANN and CNN and other algorithms that is there in the market? I mean, how do you foresee it will overtake the other things?
I think it takes some time, most probably in another 5 to 10 years time, because 2030 only everything would be possible. So in the meantime, I think we can work with that. And once the better things comes, maybe we can try to use the better thing. And we don't know. Even I think we can see more and more better algorithm than SNN also can come more than the, maybe we can bring out an algorithm which is powerful, more powerful than our brain. Maybe in future, anything is possible. Okay, so that's why nothing has been. We can predict anything here. And the most probably in another 5 years' time, we can see definitely this energy efficiency will be a very, very typical issue. Not only in the telecom area, almost in all the other area like a supply chain or no, but now I see Flipkart or Amazon, huge data. So they wanted to process the huge data with lot of servers and other things are available. So this is better to run this type of energy efficient algorithm, so that I think we can see this type of algorithms can come out and then it can be used in this areas. But neuromorphic hardwares are little bit takes time, because there are a lot of researches going on to preparing it. We're already running it, the algorithms running under the hardwares, not that much. They are doing a lot more efficient manipulations to make that hardware and more effective. It takes some time.
Thank you, sir. Thank you for
Sir, how they are related with the quantum computers?
Yeah, that is another interesting thing. Actually, we are also working on. I'm working on a quantum computing area also. The quantum also 2030 only will get the quantum hardware. Till now, we are working only on the NISQ or no noise controlled of things or simulators or most probably like a very little qubits availability of the hardware. They are generating it like an hybrid quantum computing models. So this is another thing that is also parallelly quantum computing and the neuromorphic computing are the two different future areas which are working. Now people are trying to combine these two areas called the quantum neuromorphic computing. So they are building the model instead of the neural network. They are quantum LIF models they are trying to build, and they are trying to optimize those things which they are trying it now. Still, it is working under the conventional machines, not anything on the neuromorphic hardware or anything on the quantum hardware. So there has already been research is gone, but energy efficiency, this is brain-inspired models are very, very effective, and quantum is also is good for a parallelization, and energy efficient is not comparatively better than this. This type of models are much better compared to the even the quantum inspired models.
Is there any application in the area of edge computing, cloud computing about this this area?
Edge intelligence. You can run this type of models there, because edge is only we need a lot of power. So how we can able to use this type of the algorithms, I think neural network models in the edge intelligence. One of the application which I shown is actually the person wearing a lot of different devices, and how it fastly calculates, gives all these things. This type of models are very, very effective. Edge intelligence SNNs are very, very useful for edge intelligence.
Thank you, sir. Thank you very much.
So I think I'm in a time, sir. I think I almost completed on, because it's almost very late. I don't wanted to take much time also to the people.
No, it is correct.
I think they should enjoy this. That's why I think, because this is a little bit very advanced, but still I think they can get into that. And then somebody, if you are really interested to do a research on this area, this is very one of the potential area they can able to undergo for a research and then publish more papers on this area.
Correct. So I think Sarah has already shared the email. I mean, if you have any questions to interact with Sir, you can always mail him. So once again, we'll thank Dr. Saravanan for sharing the, very advanced knowledge, of course. And very useful. In fact, basically nowadays this energy efficient algorithms are very popular. It is essential, in fact. So then we will close the session. So we'll meet again tomorrow. For the session starts from 2 p.m. because tomorrow is Saturday session. So then it will be going for 3 lectures and then followed by test and all. So anyway, we'll thank to sir, and participant, if please can wait, and you have any queries on regarding the tomorrow test and feedback, etc., we'll discuss, and any queries you have, then I will answer you.
Thanks for the opportunity. Thank you, sir. Thanks for this opportunity. And people, I think, really enjoyed this. Maybe with learning some more advanced concepts. Keep enjoying. Thank you. Bye.
Thank you, sir. So regarding the tomorrow session, so like today we have lecture by Professor Sivaram Ambikasaran from IIT Madras Data Science Department. Due to his health issues and all, so he was unable to join today, and I am really greatly thankful to Dr. Saravanan sir, who agreed instantly to prepone the lecture. And it's really generally we never request any speaker to prepone lectures. It's a very difficult task. So fortunately he agreed, and we are really thankful to him. We are trying to keep in touch with Professor Sivaram Ambikasaran. If he will be agreeing to give the talk tomorrow during the sessions where the Saravanan sir was is about to give 3:30 to 5 p.m., then he will give that time. Or in case suppose he won't be available, then we'll arrange an alternate speaker, maybe new speaker, or maybe the speaker who already whose session is already there, or one of the existing speaker. That we will discuss and discuss with the speakers and finalize that with ATAL FDP approval. We're in process of that. So okay. I would like to request one more thing, that I request few participants to give their feedback during the tomorrow sessions. We have a feedback sessions after the test. So kindly, I would request the participants tomorrow during the feedback session gives a 2 to 3 minutes feedback, your experience, overall session, and any specific sessions you feel interesting, or any class of sessions you are really interested. That will be really help to improve in future. That also will give us an idea that how can be. Of course, the different people have different perspective, but we'll try to make the summarize the perspective from multiple opinions. So kindly come up to give feedback sessions, more than 3 people maybe, and give 2 to 3 minutes overview of the things and what your experience you have received. And that is one point. When you give the feedback, then that is one concern, that as per the AICTE total program, you please introduce yourself before giving the feedback, so that will be help to the AICTE as well, that you are the participant and you have certain concerns. Okay, so kindly introduce yourself, then give the feedback. That will be really grateful. We really be helpful for us. Again, one more point I would like to add, that you have a test tomorrow, and video. Okay, yeah. So basically, yeah. So whenever you give the presentation, one more point just I would like, I forgot it. That point is that you please switch on your video. So your face will be visible, and give a feedback. Please kindly voluntarily come forward and give the feedback. So we should not call anybody, like that. Please voluntarily come and give the feedback with the video. Okay, so one more point, that about exam. So tomorrow we have the exam session, the test session. That will be Google form based. There will be total 30 marks, and we will provide you 45 minutes. And this is MCQ based questions, and there won't be any multiple answers, but only single answer will be the correct answer out of the 4. So no negative marking. And the most of the questions are very general concept questions based on the talk only. So the lectures that you have came across, based on that, more general perspective questions we'll try to figure out, and that will be there. So you need to score probably 80%, right? Sanjit, I think Sanjit will be there, right? Yeah. We note that the ensuring the certificates 80%, attendance required 70%. Okay, fine. 80% attendance, 70% mark to in the test. That is mandatory as per the norm. So attendance is as I just say that there is automatically attendance taken by the Google, the Google Meet. So we will record that. So that will be there is the complete proof with us. So there is no problem. So we will send it. We'll update it on the portal, and again that will take care. So all of you can attend the exam. So based on attendance, we will shortlist them. But all of you please attend the test. Test time is at it's 5 to 6:30, right? I think. Let me check.
Yeah. So tomorrow 3 sessions are there, 3 technical sessions are there. So we will finish all those 3 technical sessions, and after that we will do participants feedback and quiz. So that is what is the tomorrow's agenda. So most probably test timing will be around 6:45 to 7:30, something like that.
Yeah,
Okay.
so 6:46. 6:30 is the schedule. So 6:45 around it will take time. Yeah, true.
Yeah.
Correct. Yes, correct.
Any other questions? Okay. Sir, I think there is no question, so maybe we can end the session.
Oh, yeah. Okay.
Yeah.
Okay. Thank you all. We'll meet tomorrow then. Please join tomorrow exactly before. Just 10 minutes before 2 p.m. So the sessions are very important because the first session will be by my IIC Bangalore, the professor by Yogesh, and then the middle session I will just figure out if the IIT Madras data science professor Sivaram Ambikasaran will agree, he will be there. Otherwise, fine. And third session will be very much interesting, and it will be by the IBM US research person. He's also bearing a very strong background from IIT background, and also did PhD from US and Georgia Tech, hopefully. So these are good talks are there. So please be present Saturday for all 3 sessions, and then so followed by the test and all. Okay. So we'll close the session. We'll meet tomorrow.